Hi. So, look, we've been talking in depth the theory and intuition behind calculating slope of the derivative of the function using derivative, and how to find minimum and maximum of the function, and how to describe the function, whether it's concave or convex. So now it is a time to see this in practice. Okay, so look, let's just say that our first task is to draw this function. Now, how do you approach it? Look, of course, we're going to use derivatives. So first thing I'm going to do is to calculate f prime of x. Okay, so it's 3x squared minus 6x. Now, where will I find zeros, where will I find maximum or minimum of this function? Well, I will find it at points where this derivative is equal to 0. So let me just solve this equation, and it will also allow us to draw this parabola. Because look, I can easily divide both sides by 3, so I'm getting that this is x squared minus 2x, right, equal to 0. So this is x times x minus 2 equal to 0. And look, in this case, of course, x is either equal to 0 or x is equal to 2. Okay, so look, now I can make this additional graph, not of the function, but of the derivative. Look, I know that this is parabola. Because it has positive coefficient over here, it will have its ends up, and I can now draw the parabola. I know it goes through 0 and 2. Okay, and here we have f prime of x. Okay, so look, what have we learned from it? We see that derivative from negative infinity to 0 is positive. Wait a minute, very bad. X. And from 2 to infinity is also positive. On the other hand, between 0 and 2, it is negative. Okay, so what is this telling us? Look, I can divide this area and conclude a couple things about our original function, f of x, just based on the value, based on the sign of the derivative. Look, here, because derivative is positive, it means that our function has positive slope, which means that our function is increasing. Over here, derivative has also positive slope, which means that our function here is also increasing. Over here, derivative is negative, which means that our function over here is decreasing. Okay, so what can we say now about these 2 points? Look, here function goes up, has 0 slope, and starts to go down. Then this point is clearly going to be a maximum. Here the function goes down, reaches a 0 slope, starts to go up. This point must clearly be a minimum. But before we go to join the function, let's get down to the second derivative so we know everything in a little bit more detail. Okay, so look, now I'm going to calculate second derivative. So what am I going to do now is simply to calculate the derivative of the first derivative. And look, I'm getting that this is 6x minus 6. Look, this is a simple linear function. Again, what interests me in this case is at which point it cuts through x-axis, right? So I'm equalizing this with 0, and I get that 6x equals to 6, or x equals to 1. So, if I'm going to draw this, this function, it will go through 1 over here on x-axis. Here we will have f piece of x, and it will be upward sloping function like that. Okay, so now we see that this function, our second derivative, is negative over here, and it is positive over here. What does that mean? Well, this means that over here, our function has negative acceleration. What does it mean? Of course, it needs to be concave. Over here, the function has positive. Of course, remember, this is about the function. We talk about this one based on the second derivative. Now, because second derivative is positive here, then the function must have positive acceleration. So the function must be convex. Okay, so there's only one more thing missing to finally draw a graph here. Well, we need to find the values for our point of interest. What are those? Well, clearly 0, 2, and 1, right? So, first, f of 0 is equal. I'm just substituting 0 instead of this, 0 instead of this. I'm getting that this is 2. Then, f of 1, I'm getting that this is 1. Then minus 3 plus 2, which clearly is 0. And then I need to calculate f of 2, which is 8 minus 3 times 4, 12, plus 2, which gives us negative 2. Okay, and all this information that we've got over here will allow us to draw a beautiful graph of this function. Okay, but look, we're going to do it very, very slowly because we're doing it for the first time. And let's put all the information that we had from this below our coordinate space. Okay, look, we have 3 points of interest: 0, 1, and 2. Okay, and look, first let's put this information. We know that the function from negative infinity to 0 is increasing. Then we know that the function from 0 to 2 is decreasing, and from 2 to infinity is again increasing. But look, this is not all the information we have. Because look, additional thing we know is that let me just draw it like this. From negative infinity to 1, the function is concave. Then, from 1 to infinity, it's convex. Okay, so I think at this moment we are ready. To draw the function. Okay, so here what I can see is that the function is increasing. Oh, one more thing. Let's put our points of interest. I would forget about this. Now, so first, if f is equal to, if x is equal to 0, f is equal to, and y is equal to 2, then if x is equal to 1, y is equal to 0, and if f is equal to, x is equal to 0, then y is equal to negative 2. Okay, so first, look, over here, we see that right up till 0, function is increasing and concave. Then, what happens is the function between 0 and 1 is still concave, but now it's decreasing concave, which means that it will look like this. Then, the function continues to decrease, but now in a convex manner. And from this point on, it's of course still convex, but now increasing. Okay, and look, what is this point? Of course, this point is our relative minimum. This point is our relative maximum. And what is here? You look, the function stops being concave and starts being convex. So this point must be inflection point. Okay, and look, this is how we use the information conveyed in derivatives in order to draw a function. Okay, let's get to another example. The next one is actually going to be easier. Okay, give me just a second to erase the blackboard. Okay, so now we've got negative 2x squared plus 8x plus 25. Okay, so again we start by calculating first derivative. And the first derivative in this case is negative 4x plus 8. Again, we are interested in at which point this function is going to be cutting through x-axis. And now look, we see that this is negatively sloped linear function. All we need to do now is to find where it is equal to 0. So we get that this is negative 4x equals to negative 8, or x is equal to 2. So if I'm going to draw this function now, here we have f prime of x, here we have x, and we know that it cuts through x-axis at point 2, and it is downward sloping, so it goes like this. Okay, so what do we see now? We see that derivative here is positive, right up to 2, and then over here it is negative. What does it tell us? Well, here the original function is increasing, while here the original function is decreasing. Okay, so we already know a lot, but let's now go to the second derivative to find out even more. Okay, so we've got that the second derivative, which is a derivative of the first derivative, we get that this is just negative 4. So look here, the case is very simple. we've got, if here we have f piece of x, and here we have x, then this function is a constant function at -4, and look, because this function has, because second derivative, it's always negative, it means that this function is everywhere concave, right? Because it has negative acceleration. So this function is concave f. Okay, so now in this case we've just got one point of interest. This point is 2, and we've got that y that f of 2 is equal to 4 times -2 is -8 plus 8 times 2, which is 16, and plus 25. This is giving us 8 plus 25, 33. Okay, so what do we need to do next? Now we are ready actually to draw the function. And let's also put all the information that we got from these two graphs. Okay, so here we've got x, of course, here we've got y. Now, we've got just one point of interest. Point of interest is at 2. And we know that when x is equal to 2, y is equal to 33. Okay, what else do we know? We know that over here, so from -infinity to 2, the function is increasing. Then, from 2 to positive infinity, the function is decreasing. And we also know that it is everywhere concave. So it should look like a cave, right? So here, right up to 2, it's increasing concave. And then from this point on, it is decreasing concave. Now, how much do we have here? Well, if x is equal to 0, then y is equal to 25. And here, this point at the top is a maximum. Okay, that one was actually way easier. Now let's get back to a case that is slightly more involved. So, now, we've got x to the power 3 plus 6x squared plus 9. You know what? I'm going to change one thing here, actually. To make this case a little bit more interesting, let's change all the minuses, all the pluses to the minuses. You'll see actually where I'm going with this. Why did I do it later? Okay, so now we start as we always do. F prime of x is equal to -3x squared minus 12x. And again, this is a parabola. It will be cutting through x-axis in 2 points. So let's find those. First, I can divide both sides of this equation by negative 3. So I get that this is x squared plus 4x. Right? Right. Okay, equal to 0. Okay, so now the next thing I can do is to take x out, and I'm getting that this is x plus 4 equals to 0. Out of this, I'm getting that x is either equal to 0 or x is equal to negative 4. Now, I need to draw a parabola again. I'm going to draw it a little bit to the side, just to make it a better graph. And look, one thing is different here. Look, our parabola now has a negative coefficient, which means it's going to have its hands down. So it's going to be going through. It's going to be going through point negative 4 and through point 0. And it's going to look like this. Okay. Now, what do we learn out of this? That, look, between negative infinity and negative 4, function has a negative slope, which means that the function is decreasing. Then, between negative 4 and 0, the value of the derivative is positive, which means that in between those two values, our function is going to increase. And finally, over here, derivative is again negative, which means that the function is decreasing again. Okay, so now let's go to the calculation of the second derivative. Okay, second derivative is equal to negative 6x minus 12. Okay, again, we want to know at which point this function cuts through the x-axis. So we get that negative 6x equals to 12, and we get out of this that x is equal to negative 2. Now, we see that this line, that this function clearly has a negative slope. So, if I'm going to draw it, I'm going to put negative 2 over here, and it's going to be looking something like this. Here we have f b's of x, and here we have x. Okay, now, what can we learn from this case? Well, here, we see that the second derivative is positive, which means that our function here has positive acceleration, which means it's convex. Over here, second derivative is negative, so from this point on, the function starts to be concave. Now, we've got 3 points of interest. Those points of interest are negative 4, 0, and negative 2. Okay, let me calculate those. First, f of 0 is very easy in our case, it's just negative 9. Then, f of negative 2 is, okay, so here we've got negative 8 with minus, this is 8. Then we've got 4. Then we've got 4 times negative 6 is negative 24 and minus 9. Which gives us negative 25. Okay, and then we've got f of negative 4. Oh my god, this is going to be unpleasant. But, okay. So we've got 4 times 4, which is 16, times 4, which is 64, negative 64, but with minus, which gives us 64. Then we've got 16, we've got 16 times negative 6, which is negative 96, and minus 9. Okay, so out of this we get negative 32. Negative 32 minus 9 is negative 41. Okay, so now let's put all those points on the graph. Okay, so there's x-axis, there's y-axis, up, and we've got, sorry, I always like drawing this part bigger, like force of habit, but now we are interested in this part. Look, so here we have 4 points. First one of point of interest is negative 4, then there is negative 2, and then it's 0. Now, we know that if x is 0, then y is negative 9. We know that if x is negative 2, y is negative 25. Then we know that if x is negative 4, then y is negative 41. Okay. Now, okay, I don't have enough space, but I think from our experience, we can already see what is going to happen. Look, from negative infinity, so negative 4, function is decreasing in a convex manner, which means that the function will look here like this. Then the function starts to increase, but still in a convex manner, which means that it's gonna look like that. Then the function is still increasing, but now in a concave manner. Let me put this minus 9 over here. It's gonna look better now. Okay. And then the function starts to decrease from 0 in a concave manner, like this. Okay, and we clearly see that here we've got a minimum, here we've got maximum, and here we have inflection point. Okay, so I think we've mastered the art of drawing of cubic function. So now let's try something different. Now let's try to draw a reciprocal function. Well, again, by using first and second derivative. And look, the thing is that very often we don't need to calculate everything step by step, but sometimes we just need to assess the sign. And I'm going to show you this in this example. Okay. So our function is x plus 2 over x minus 1. Right away we should notice that in this case x must be different than 1. Which is of course important. We cannot calculate anything at this point. Okay, so first thing we do, we need to calculate first derivative. Okay, what do we need to use here? Of course we need to use quotient rule. So, in quotient rule, we've got x minus 1 squared, and now, derivative of the first expression, which is 1, times the second expression, which is this expression in the bottom, and now minus the first expression times the derivative of the expression at the bottom, which again is 1. So look, out of this we're getting that this is x minus 1 minus x minus 2 divided by x minus 1 squared. Right? Now this x, out of this, two x's are cancelling each other out. We are left with negative 3 over x minus 1 to the power of 2. Okay, look, we are usually interested when derivative is equal, when the derivative is positive, where the derivative is negative. Now, can this expression be equal to 0? Well, no. Maybe in limit, right? If this number in the numerator would be extremely big, we would be getting closer and closer to 0. But in principle, it can't, right? And look, we are dividing negative number by a positive number because it doesn't matter what is in square. Of course, it cannot be 0, but we excluded this right away. We will get a negative number, so we can be 100% sure that this is lower than 0. And look, if first derivative is always lower than 0, it means that our function is always decreasing. Okay. Then, let's move on to the second derivative. Okay, so look, now we need to differentiate expression negative 3 over 1 minus, x minus 1 squared. And here again, we need to resort to the quotient rule. Okay, so we're going to start by taking whatever is in the denominator and putting it in the bottom with squares. So we're going to get x minus 1 to the power of 4. Now, how do we approach this later? First, derivative of the expression on the top times expression on the bottom. But this is 0, right? Because derivative of a constant is 0. So we will have here 0 and then minus. Expression on the top, which is negative 3. Okay, I'm going to write it. And times derivative of this. Now look, in this case, in order to calculate derivative, we need to use the chain rule, right? Derivative of the function inside is 1 times derivative of this, which is 2 times x to the power negative 1 to the power of 1, right? Okay, so what are we getting out of this? This minus and minus gives us plus, so we've got plus 3 times 2, this gives us 6. 6 times x equals 6 times x equals 6x, and 6 times minus 1 is equal 6. Now, we can ask what will be the value of this expression, right? And look, this expression can take both positive or negative values, but we still know that expression in the bottom will always be positive, right? Because we excluded 1. So the only thing we need to find is where 6x minus 6 is positive or negative. Look, this we can get again by noticing that this is a simple linear function with positive coefficient, which cuts through 0 axis when x is equal to 1, which means that this function is going to look like that. And again, we see that because here here the function is positive. This function is positive. Let me just show you this is second derivative. It's positive. Then the function here must have positive acceleration and be convex. On the other hand, over here, the function, second derivative is negative, so over here it has negative acceleration, it must be concave. And now we have everything we need to draw it. Maybe, one last thing could happen. Look at our function. Our function is x plus 2 over x minus 1. Look, this is the same as x minus 1 plus 3 over x minus 1, right? Minus 1 plus 3 plus 2. But this is the same as 3 over x minus 1 plus x minus 1 over x minus 1, which is equal to 3 over x minus 1 plus 1. Look, remember we were dealing with this. This is showing us that this function is going to have an asymptote at 1. Okay, so now let's get to drawing. Okay. So. Okay. Now, first we notice that of course we cannot calculate value at x equal to 1, but our experience with the reciprocal function tells us that this means that at x equal to 1, there's going to be an asymptote. And also, we've established that we will have another one at 1, but this time on y. So these two asymptotes will help us draw this function. And okay, what else do we know? Look, we know that this function everywhere is decreasing. Because we found out that this function has constantly negative first derivative, of course, not including point 0 and point 1, which is out of the domain. Then we found out also that from negative infinity to 1, the function is concave. And from 1 to infinity, the function is convex. So, how will this function look like? Look, over here, it is decreasing concave. Over here, it is decreasing convex. And look, this is exactly the shape we've got in our previous exercise, in our previous classes, when we were manipulating the shape of the reciprocal function. Okay, I think this is enough when it comes to examples. In the next video, we're going to see some economic application of optimization techniques. Okay, thank you and see you in the next video.